Hello, everyone. Welcome to CON304. My name is Mridula Grandi. I'm a senior leader with Worldwide Specialist Organization in Amazon Web Services. And joining with me is Vibhav.
Hey, everyone. Glad to meet you, and thanks for joining us today. My name is Vibhav. I'm a senior product manager with Amazon ECS. I've been with ECS for over 3 years now and have spent my time looking at all aspects of the deployment and application lifecycle in ECS. Super excited to share what we've seen over the past year with customers starting to build and deploy generative AI applications on ECS.
Thank you. Our talk today is going to mainly focus on important themes, developing and deploying generative AI applications at scale using AWS serverless containers. And hopefully, a takeaway from this session, you will be moving forward and pacing through your GenAI journey more confidently and have enough resources to do so. But generative AI represents a paradigm shift in the artificial intelligence, empowering computers to go beyond computation and actively contribute to the process of creation. At its core, generative AI is about machines that can imagine, innovate, and produce entirely new content. By incorporating sophisticated algorithms and deep learning, the generative AI systems can learn from vast data sets to understand structures and identify patterns. Generative AI unlocks new possibilities and creates significant business value in 4 different regions or areas. When it comes to creating new customer experiences, generative AI analyzes customer data and creates personalization for their products, services, and marketing messages. This helps in enhancing the overall experience and improves customer satisfaction. Generative AI can enable builders by bypassing time-consuming coding tasks. For example, by using Amazon Code Whisperer, builders can complete their coding tasks 57% faster, thereby boosting employee productivity. Next is creating content. We have recently launched Amazon Party Rock to create applications, and you don't even need to know how to write a single line of code to do so. Generative AI has the ability to analyze extensive data sets and create insights by which you can make predictions faster and take informed decisions. When it comes to generative AI transforming various industries, let's look at some of them and what their use cases are. To start with, financial services industry, algorithmic trading is one of the commonly used strategies in the financial services industry to speed up and make it more efficient. Now, it's typically a complex process involving a deep understanding and a combination of domain expertise on market vectors as well as financial segments, as well as technical knowledge in terms of how to build the automation and incorporating the logic. With GenAI, you can analyze market data to automate the trading strategies and predict market sentiments quickly. Now, its ability to generate alerts for potential fraudulent activities is also one of the predominant use cases that we're seeing customers in the financial services industry handle risk management proactively. Now, within healthcare, generative AI has been transformative in terms of medical imaging diagnosis as well as drug discovery. Now, in the automotive and the manufacturing industry, generative AI models have enabled to optimize supply chain logistics, including inventory management and warehouse operations, as well as detect defects to ensure product quality. Now, in the educational sector, with generative AI, our customers have been able to create digital learning platforms with intelligent tutoring systems that can provide adaptive assessment on the fly based on each individual student's pace and progress. Now, with all of this, one would wonder, what does a GenAI tech stack look like, and what does it entail? The tech stack for a GenAI application typically has 3 macro layers, and these layers work with each other, talk to each other, and enable the pipeline of development and deployment of the applications. To start with, we have the data layer. In this layer, data is collected from multiple sources and stored in the data warehouses, pre-processed, cleaned to ensure its quality, and the noise is removed through normalization techniques. Then you annotate the data and label the data, thereby making it ready for training purposes. The second layer is the modeling layer. In this layer, you choose the specific machine learning or deep learning algorithm, depending upon the nature of the problem that is being solved. And then the selected model is then used against the pre-processed data and trained. During the training, the model learns to make predictions, and then the model is then validated against new data, and it's just iterative from there. In the deployment and application layer, the model is deployed onto production environment and integrated into the application to perform specific tasks, such as make predictions or generate content and so on. Now, coming to the roles in the generative AI ecosystem, there are three main roles that create a pipeline that goes from development and tuning to the deployment and visualization and utilization of the generative models through APIs. Let's take a look at each of the roles and their skill sets. To start with, we have the model provider. The model provider is typically responsible for creating or offering the generative models used in the system. This role involves designing, training, and potentially fine-tuning the generative models. Model providers can be individuals or organizations that start building the foundation models from scratch. Now, this role involves a diverse skill set, including machine learning, deep learning, programming, and domain-specific knowledge on data science for pre-processing and augmenting the data. Second one is the tuner. The tuner role involves optimizing and fine-tuning the generative models to enhance the performance of the model. And then tuning may include adjusting the hyperparameters, refining the training strategies, or adapting models to specific use cases. Tuners work closely with the initial models provided by the model provider and iterate on top of it to improve its capabilities. Now, the typical skill set that is required for tuners is having a deep understanding on machine learning algorithms and having also an understanding on hyperparameter tuning and tuning strategies, as well as prompt engineering. The last role is the consumers. This is where the consumers actually take the models and integrate into the applications, either via the APIs or directly consuming through the APIs. And the skill set that is required for consumers is to be able to work with the APIs and SDKs and frameworks such as TensorFlow or PyTorch. Now, keep in mind in an open source community, individuals can be performing multiple roles. For example, researchers can be providers as well as tuners, and similarly, developers can be consumers as well as tuners. Now, building foundation model involves several considerations. To start with, training foundation models often requires significant computational resources. Access to these resources can be a barrier if it's not planned properly. Second, building foundation models can be a time-consuming process, and the training time depends on various factors such as model size, its complexity, data size, and its diversity. Secondly, hiring the right talent is always a challenge, especially when you need a blend of domain expertise of AI/ML, deep learning, and technical skills on algorithms and building automation using various frameworks. Lastly, optimizing the use of resources, both in terms of computational power and memory, is crucial. And developing models that are efficient in terms of energy consumption and computational costs would require an ongoing effort, and it takes time. Now, AWS customers have asked us how they can quickly take advantage of what is out there today and be able to use foundation models and create their generative AI applications within their businesses and organizations to drive new levels of productivity and transform their offerings. We identified 4 key considerations for you to be able to quickly build and deploy generative AI applications at scale. We will be double-clicking on each of these key aspects for the rest of the talk today. The first is we have a thorough understanding on foundation models. Foundation models have been playing a significant role in advancing the state-of-the-art in natural language processing and machine learning. A foundation model refers to a large, pre-trained artificial intelligence model that serves as the starting point for a wide range of downstream tasks. Few commonly known foundation models are BERT, GPT, and T5. These models are typically trained on extensive and diverse unstructured data to learn general patterns and representations across various domains. Foundation models are often massive in terms of parameters in the order of hundreds of billions and typically require large-scale computational infrastructure to run the training on these models. When it comes to the types of foundation models, there are 3. First is the text-to-text large learning model. Many organizations have had a chance to experiment with the generative large learning models that can do things like summarizing text, respond to questions, extract information, and create content. These models take the user's input text as prompts and extend it with new generated text. Second, there is a text-to-embeddings LLM that can compare pieces of text, like what a user types in a search bar, and then it compares with the index data and connect the dots between the two. For example, we have Amazon's OpenSearch that uses this type of large learning model where it compares a user's ask against catalog of data, and it presents the user with more accurate and relevant results. Also emerging are the multimodal LLMs, where the foundation models can understand text as well as images. An example is the Stable Diffusion Foundation model that can generate images based on a user's natural language prompts. Now let's take a look at how a foundation model is built. Normally, you would start with your machine learning process because you have a business problem and you identified that machine learning is the way to go. Then a data scientist collects all the data from multiple sources and integrates data from the various sources, cleans the data, and analyzes the data. Next, the data scientist starts the process of feature engineering, training, and making sure the models are tuned and evaluated the performance of those models. Based on the results, the data scientist might go back to collect more data or perform additional data cleaning steps, but assuming that the models are fundamentally performing well. And then they would go ahead and deploy the model so it can be used to generate predictions. The next step is basically an important one, is to monitor the model which is in production. Now keep in mind, a machine learning model is out of date as soon as you've trained it. And the world is constantly changing and evolving, so the older your model gets, the worse it gets at making predictions. So by monitoring the quality of your model and making sure that it's being retrained with the new collected data to adapt to its changing requirements or changing patterns is important. The final but very crucial one is to be able to build your model responsibly and making sure that it's incorporated across every step of the workflow is going to be super crucial for your businesses. Let's take a look at how AWS has been building our generative AI offerings responsibly. With Amazon Code Whisperer, you can build applications faster and more securely. We have something called an AI coding companion. It has inbuilt security scanning for finding and suggesting remediations for hard-to-detect vulnerabilities. Similarly, we have the Amazon Titan Foundation models. It consists of 2 new LLMs for text summarization, text generation, classification, and information extraction. They are also built to detect and remove harmful content in the data that customers provide for customization, reject inappropriate content in the user input, and filter the model's outputs containing inappropriate content. The second key strategy or consideration to accelerate your GenAI journey at scale is to use the pre-trained models wherever applicable. A pre-trained model is a machine learning model that has been trained on a large data set for a specific task and is saved or distributed for reuse on new and specific or related tasks. Now, some pre-trained models have gained widespread popularity due to their effectiveness across various tasks. The models that you're looking at the screen right now are a broad selection of open source models that offer many capabilities, including natural language processing, image generation, and text classification, such as summarization, sentiment analysis, and information extraction. With SageMaker Jumpstart, ML builders can choose from a broad selection of open source foundation models. And Jumpstart offers the ML practitioners who want to have the deep model customization and evaluation capabilities to access the foundation models through environments that they already use, like SageMaker Studio or SageMaker SDK and the Amazon SageMaker console. And we have new models added on a weekly basis. Next, in the model development, there's also an approach called fine-tuning, which takes the pre-existing models for specific tasks and tunes it further for domain-specific tasks. This involves taking a pre-trained model and adapting them to a specific downstream task or domain. Fine-tuning involves further training the pre-trained model on a specific data set, which is typically smaller than the original data set and focused on a specific domain or a task. Conventional fine-tuning or full fine-tuning involves updating all the model weights based on the new data set, while full fine-tuning of all layers provides optimal results. It is resource-intensive and can be prone to forgetting original information. So to that, we have the performance-efficient fine-tuning, which is PEFT, and a flavor of that is LoRA, is low-range adaptable model, which takes 2 or 3 matrices and basically tunes with the equal amount of performance and efficiency. Now, one would wonder, when would I choose to pre-train versus fine-tune? And while these two approaches are 2 stages in the life cycle of tuning or using a pre-trained model for a specific task, pre-training involves training on a large and diverse data set for a general task, while fine-tuning involves further tuning on a smaller task-specific data set. Pre-training can be computationally expensive and time-consuming due to the large data set, versus the fine-tuning typically requires less time and resources compared to the pre-training, since the model starts with pre-trained knowledge. In real-time scenarios, the combination of pre-training and fine-tuning is a powerful approach, especially in the deep learning, where pre-trained models are often used as a starting point for tasks with smaller data sets. This strategy leverages the advantages or the benefits of capturing general knowledge from large data sets while adapting the model's knowledge to a specific task. The other evaluation criteria that you would want to consider is, when would you want to choose the foundation model versus the pre-trained model? Choosing a pre-trained model and building a foundation model depends on various factors, including the specific requirements of your task, the available resources, and the nature of your data. If your task has specific requirements that differ significantly from the task's pre-trained models, then building a foundation model from scratch may be more suitable. Additionally, if you have a large task-relevant data set, training a model from scratch allows you to learn the features directly and related to your specific task, potentially leading to better performance. Building a foundation model provides full control over the model architecture, and this is beneficial if you need to design a model with specific architectural considerations that are tailored to your business statement. Now, to sum it up, here's a few best practices to build generative AI responsibly. These best practices will continue to evolve, but here are some key points that we'd like to share that we've learned so far. First, focus on your use case. How you're defining your specific use case is going to be directly relational to developing your training algorithms that enforce that definition of the problem statement. Second, prioritize education and diversity in your workforce. For example, in terms of human annotated training data, promoting diversity in the actual annotations is key. And the third is we want to make sure that we assess the risk because each use case has its own unique set of risks. Fourth is test, test, and test. Each use case would have its own performance evaluation, and oftentimes it just takes as much time to come up with a testing system as much as it would take to create the model. Next, continuously iterate across the AI lifecycle, and then make sure that you are introducing governance policies with accountability and measurement through each step of the workflow. The third is the utilization of cloud services is going to be highly beneficial for generative AI applications due to the specific demands and requirements of a Gen AI development, training, and deployment. Whether it's the computational power of training complex generative models or scalability to make sure that your computational resources are scaling on demand, or storing huge data sets with efficient retrievals, and many other benefits like security, monitoring, cost efficiency, it just gives you a good playground for experimentation. And leveraging cloud services for Gen AI processes or applications provides access to this powerful ecosystem of resources. Here's how our generative AI offerings come together. We have the first layer, which is the Amazon Bedrock, the easiest way to build and scale generative AI applications with foundation models like Anthropic, Stability AI, and even Amazon Titan models. Amazon EC2 Inferentia and Trainium gives you the best price performance infrastructure for training and inference in the cloud, and AWS Trainium and AWS Inferentia combined with EC2 Ultra clusters and high-speed networking will give you the bandwidth and the computational power that is required to build and train your generative models. We have services with inbuilt generative AI, such as Amazon Code Whisperer, AI coding companion that helps you build applications faster and more securely, and it's free for individual use. Next, with the deepest and broadest offerings, AWS provides a platform that combines speed and power to give you the agility to move quickly when it comes to rapidly pacing through to accelerate your time to market when it comes to building generative AI applications. Speed in the form of serverless computing that allows you to execute code without having to manage the underlying infrastructure. And Amazon's power of generative AI offerings like SageMaker Jumpstart, ML practitioners can choose from the broad selection of open source foundation models where new models are added on a weekly basis. Now let's double click a little bit on the serverless operating model. The serverless operating model enhances the development and deployment of generative AI applications. It provides a flexible, scalable, and cost-efficient environment. It aligns well with the event-driven, modular, and scalable nature of the generative AI tasks, allowing developers to just focus on creating generative AI applications without the burden of managing infrastructure. Serverless applications are event-driven, responding to events such as data uploads, user requests, or scheduled tasks. This aligns well with the generative AI applications where events like data availability or user interactions can trigger more training on inference tasks. The abstraction that serverless provides is beneficial for builders building generative AI applications, allowing the developers to just focus on model development and application logic.
We'll spend a bunch of time talking about how you would actually go about first developing and building an AI-powered application and taking it into production. So a good place to start is by actually asking yourself, do you really need to use generative AI for this application? Please don't get me wrong, generative AI is a game-changing technology, and we're seeing customers start to use generative AI in all sorts of creative ways. But given the level of hype around generative AI at this point of time, it is easy to fall into the trap of trying to overfit your problem to use generative AI, even if using Gen AI wouldn't materially help customers for that particular use case. And a good way to evaluate whether your application aligns with use cases supported by generative AI is to define the use case that you're looking to solve and see if it really needs any of these capabilities. So depending on whether your application needs text-to-text capabilities or text-to-imaging or text-to-audio or a mix of any of those, makes sense. Go ahead and use generative AI. But if not, it's probably a good idea to look elsewhere for building your application. Now, once you know that you actually need to build, you want to build a Gen AI-powered application and you have validated the use case, the next thing you want to probably do is figure out what model you want to use for your application. Now, even before you can choose that application, choose the model that you want to pick, a good question to answer is, how do I actually measure what is a successful model versus what is not a successful model, because there's so many foundational models available right now from so many different vendors. So this is a good heuristic way to reason about this. A good first question to ask is, does label data even exist for the use case that I'm trying to vet for? If it does the use case actually end up in providing discrete outputs and outcomes? If so, great. You can have a very high precision accuracy metric that you can measure to evaluate different models. But unfortunately, not a lot of use cases for generative AI actually have high precision metrics that you can use. An alternative would be similarity metrics. So you compare the response that the generative AI model is giving versus what would be an ideal response, and that you could use that to see if the model is performing well or not. Now, if labeled data simply does not exist, then the question to ask is, do you want to even try to automate the process or just evaluate it manually? And if you realize there's no way to automate this, in that case, you're probably best off just trying to comparing different models and having a human evaluating all of these options. A possible thing you could look at here is SageMaker Ground Truth. And if, on the other hand, if you do think that if you do want to automate the validation process, an alternative could be to compare the model output to an LLM or a model that you trust. This might be a little overwhelming at first sight, but let's walk through an example which might make things a little more tangible for you. So define the set of prompts that you want to test your Gen AI model against. So we've done that here, and we know what type of output we want to expect. So for some of these, we know this is the output I want to expect, and I've predefined it. But for a lot of the others, like for instance, the coding task, you might not have the output already defined. So the next step, you pick a few popular models that you want to evaluate. Things that you could look at could be Titan, Claude, Llama, any of those, depending on what your use case is. And then you evaluate all of these against what the accuracy of the model is. I will say this, if this still feels overwhelming and you don't have someone in your organization or in your team who can help, I'd recommend using Playgrounds and Bedrock to test out some sample prompts across these models and just eyeball it, see what makes sense to you, what the results from which model align the best with your expectations, and go with that. Now, once you have a clear understanding of measuring things, you want to also evaluate across a few different things. Deploying foundation models is expensive. So you want to look at what's the cost of running these. Invocations can take time, so what's the speed? How latency sensitive is your use case? How latency sensitive are your customers? So depending upon the use case, that's something that can change quite a bit. And also the precision, which we just went through. What is the most important for your use case? So and rate the models that you're evaluating across all of these three axes. So even if there's a model that is really, really high precision, but if your use case does not need that level of precision, you might be better off choosing a different model, which is slightly less precise, but is much lower cost. So in this case, for instance, you'll probably end up choosing model 2. Now, once you've decided what model you want to use, you may want to fine-tune the selected model. As Mridula already spoke through it, there's two core ways you can go about it, basically, and both involve retraining the model to some extent over a small data set. You can fine-tune it, or you can use parameter-efficient fine-tuning, which is much less complicated, uses much less data, is much cheaper. Again, if you're someone who's still relatively new to this space and you don't have someone on your team who can walk through all of this with you, my recommendation would be to actually look at pre-built capabilities in Bedrock and SageMaker Jumpstart, which allow you to fine-tune your model without actually knowing how fine-tuning actually works. In case the model that you selected isn't supported there, I'd actually suggest skipping the fine-tune step, because we'll be talking about other strategies you could use instead to make sure that your model is giving the right domain-specific output. All right. Now that we've spent a bunch of time actually talking about what foundation models are, how you can use them, how you can select them, let's come to the fun stuff, how you actually use a model to create customer value, how you create customer delight, create business value for your business. A good mental model for thinking about your generative AI-powered application is to think of the model as somewhat decoupled from your application itself. Think of it as a dependency for your application, something like, say, a database or a queue or a stream or something like that, which your application uses but doesn't necessarily have to be tied together with the model. What this decoupling leads to is a number of benefits similar to what you'd see for microservice architectures. You decouple the technology choices between what you're running your model on versus what you're building your application on. Your scaling changes dramatically. You can scale your application and your model at different rates depending on what use case you're looking to serve. And finally, because you can almost have two different teams or different sets of people focused on both of these things, you're more agile. You have smaller teams who can innovate independently and deliver and create value fast. So, and a side effect or a side benefit, I might say, of this decoupling is that you can really lean in on how you're already running applications. So for instance, if you're already running your applications on serverless compute, it becomes all that much easier to break down to deploy your Gen AI applications with serverless compute as well, once you've decoupled the model from the application itself, both physically and in your mind. So to make things more tangible, let's look at the sample architecture. I've kept this fairly simple and straightforward to keep things simple. So we have a load balancer, which is used for ingress traffic, where your end user requests are coming in. It is connected to a load balanced ECS service where your application is running. And that service basically speaks to a model endpoint. That model endpoint could be anywhere. That model endpoint could be on SageMaker. It could be on Bedrock, or you could self-deploy it on ECS. Now let's dive into this a little bit. And one particular area I would really want to talk about is how your application actually integrates with the AI model. In my mind, this is one of the most interesting aspects, especially for customers who are coming from a serverless world to start using generative AI models, because there are some nuances to how you invoke a Gen AI model. So let's go into each of these one by one. So the first question is, how do you actually invoke the model? You could naively just call the API endpoint where your model is running, but is that the best or the most efficient way to do it? Probably not. There's a number of frameworks out there. One in particular that's super popular is LangChain, which you can rely on to communicate, for your application to communicate with the model that you already selected and is deployed somewhere. A side benefit of doing this is, obviously you don't have to write integration code that is non-differentiated, but you can also switch around across models as your model, as your team that's deploying models switches to a different model, which might deliver better outcomes. And also another benefit is that the frameworks usually come with a number of getting started templates, which further help accelerate how you can deploy your Gen AI application, again, without having to write a ton of undifferentiated integration code. The next mechanical question to ask is, do you call your model synchronously or asynchronously? So a general rule of thumb to follow here is invoke your model synchronously for the most latency-sensitive workloads. So think about a chatbot, for instance. Your customer, your end user is out there, is waiting for a response. You probably don't want to keep them waiting a long time. So, however, there's flip sides to it. When you're synchronously invoking your model from your application, your model needs to scale fairly elastically to make sure that it's supporting the new load as it's getting. And that can get expensive because deploying Gen AI models is generally expensive. So stay caution. And where you can, use an asynchronous invoke pattern. Introduce a queue in the middle, for instance, which can handle back pressure. So think of a use case like, say, generating avatars or generating images, which isn't necessarily super sensitive. Obviously, you still want to deliver the best possible customer experience for your customers, and you want to keep latency to a minimum. But there is more tolerance for workloads where there is more tolerance for it. It's a good idea to invoke your model asynchronously. This allows you to set your model scaling on a much more gradual pattern, which allows you to reduce costs quite significantly depending on what the scaling characteristics of your application look like. Now that we've gone through the mechanics of invoking your model, so we know how we want to invoke the model, we know whether we want to invoke it synchronously or not. Is it fair to do we expect to get great responses for customer queries from the Gen AI model out of the box at this point of time? Unfortunately, the answer is probably not. And there's two key reasons to why this happens. One, your model, as Mridula alluded to earlier, your model is kind of out of date the day it comes out. So there are many models out there which were trained on data from 2 years ago, or they might not have access to information that your customers expect. In those cases, your model is basically out of the water because it doesn't know and it can't answer what the question that your customers are likely to ask. The other reason why this this might not work out great, is that the model might also need some feedback and tuning and guidance on style so that you can make sure that the model is speaking in the voice that you want to deliver to your customers. It's easier to walk through this with an example. So the whole discipline of prompt engineering, prompt is basically is another way of calling requests for a Gen AI model. The whole discipline of prompt engineering is all about how you annotate your customer's query with the right level of context so that your customers are getting you're delivering the right experience for customers and you're getting the right answers in the voice you want to have with your customers. So an example, and this is best explained with an example. So let's ask an AI model. So I asked an AI model, label the sentence by sentiment, think before you act. And the answer that comes out is positive. Arguably okay, but might not be what I'm really looking for. On a second try, I tried a different prompt. I said, label the sentence and give me 2 descriptive adjectives instead of leaving it super open-ended. And this time, the response that came was cautious and thoughtful, which I think makes a lot more sense for which aligns a lot more with what the intent for asking this question was. So the moral of the story here, so to say, is that don't just pass the query that you're getting from customers to your model directly. Use templates to generate prompts which you've tested out, which you know deliver better outcomes. I'm going to plug frameworks again here. If you use a framework, there are pre-built templating options there, which can reduce the amount of overhead for the amount of code that you might have to write if you're using a framework. Next up, the other problem that we still haven't tackled is models do get out of date with information. And that can be super problematic if I want to use a model that's super capable but doesn't have current data, or it doesn't have my specific data set. And a technique that's becoming increasingly popular to address this use case is retrieval augmented generation. At a very, very high level, the easiest way I can explain this is that at runtime, you fetch the right information that your model would need to answer the question, because you know your model might not answer the question. So let me run through the mechanics first, and then an example would help here. So the mechanics, so to use retrieval augmented generation, the first thing you need to do is to actually pass your the data set that you want to provide. It could be your documentation guide, or it could be some new recent events, any of that. Could pass that through a text to embeddings model, like Titan, for instance, and convert that into embeddings, and store that into a vector DB. A vector database is a recent innovation which allows directional data capture to be done much more efficiently. AWS offers managed services in this called OpenSearch for, Vector Search for Amazon's OpenSearch, as well as PG Vector for RDS with Postgres. Once you have this set up, when your customer request comes in, pass the request first to this vector database, get the relevant embeddings, and include those embeddings as part of the prompt that you send to your Gen AI model. By adding that information, your model has a lot more knowledge that it can then lean on for answering the question that your customers may have asked. So, for instance, I want to ask my model which FMs are supported by Amazon Bedrock. Now, probably because this model might have been trained before Bedrock existed, it doesn't know this. So I'm going to pass the documentation guide for Bedrock as the input here. And when I ask the question again, the model is able to answer the question because it has access to all the information it needs to answer the question. Keep in mind, there are some nuances here. Neither prompt engineering nor retrieval augmented generation actually change your model. So it's really only in the context of the particular prompt that you can lean on the context that you provided. Unlike fine-tuning, where you're actually changing weights of the model, so that every time you invoke the model after fine-tuning, it has that additional domain data. But with the RAG or prompt engineering, this is an iterative process that needs to happen every time. The other big thing to keep in mind is that the additional data or context you add is going to be limited by the context length that your model can accept. There's a finite limit to how much input your model is going to accept as part of any invocation. So you have to be fairly mindful of how much data can actually get passed as part of the invocation. Finally, the RAG is also limited by the accuracy of the embedding algorithm itself that you're using, the foundation model we use to create text embeddings from text, and the performance of the database to retrieve at runtime. This is where I think something like vector search for OpenSearch helps, because that is proven to perform much more very efficiently. Now that we have an idea of how we might want to build the application and integrate the application with a Gen AI model, let's actually talk about taking the model to production. And I'll break this across 4 different categories. First, hosting your application itself. Second, hosting the model. And then monitoring and security, which are P0 for any use case. Let's start by talking about options for hosting your Gen AI applications on serverless. As Mridula already spoke, serverless helps accelerate deployment, and that's why customers are increasingly choosing serverless containers to build and deploy all their applications. 2 prominent options that come up here are Amazon ECS or AWS Lambda. A key thing to keep in mind here is that with Lambda, and I'm sure you already know, there's a 15-minute limit on the execution for a Lambda function, whereas with ECS, this is basically unlimited. Storage is also a key thing to keep in mind. Even if you're just running the model, you're just running your application and not the model, there might be storage constraints that might pop up with Lambda, because Lambda only offers up to 10 gigabytes of storage. So keep that in mind as you choose the application. As a rule of thumb, if you have infrequent invocations, it's usually a good idea to go with Lambda, because it helps you get started super quickly. But if you expect to see fairly steady traffic, I'd lean on using Amazon ECS, just because it serves better with continuous traffic. As your application starts to see more scale, you probably want to set up auto scaling for your application. If you chose ECS to deploy your serverless your Gen AI application, you can choose to auto scale your application based on the right metric for your application. You can choose to auto scale based on default metrics like CPU or memory utilization, or you can choose based on the request that your application is saying, or any other custom metric that you want to choose. Now that we've decided how you actually want to deploy your application, a good question to ask also is how you're going to deploy your model server. At a very high level, there's kind of 3 ways you can do it. You can go the full serverless way with Amazon Bedrock, API as a service, super fast to get started. You don't need to do much to actually have a Gen AI model running that your application can call. With SageMaker, there's a full-service, fully managed platform that you can use to deploy Gen AI models, but there's still some level of effort that's going to be involved in getting up and started. Or you can go all the way and self-deploy your application, either on EC2 directly or using containers with ECS or EKS. And depending on, and this kind of boils down to a number of things. One is the biggest thing I would really lean on here is what level of expertise your organization has. If your organization has some level of expertise in running in deploying a model, It's probably a good idea to lean on self-hosted because that might turn out to be cheaper compared to something like Bedrock or SageMaker. But for most customers who don't have the right level of skill set, it's probably a good idea to start out with something like Bedrock, which allows you to get started immediately, pay per use, spin up, spin down things, test things out easily. Or use SageMaker, which gives you somewhat more configurability than Bedrock. You're less constrained on what models you can actually deploy. So it's really up to you what the right deployment layer for you is. So for ECS customers who've already chosen who are running a bunch of their applications in ECS and have some level of expertise in deploying in running Gen AI applications or have the right talent, it's probably a good idea to deploy your Gen AI model on ECS. It helps you have consistent tooling across your stack. You can deploy all your applications, including your Gen AI model on ECS. You have full scaling and concurrency control, and you get all of the rich feature set of Amazon ECS for basically free, including observability, security, scaling, and even serverless with Fargate. The next thing that you want, once you've made the choice to deploy on ECS, an immediate question that comes up would be what compute does your application need? I know for most people, Gen AI has become synonymous with GPUs, and for good reason. There's a lot of reason why GPUs are good for building and serving Gen AI models, and I won't go into those details. But it isn't necessary that you don't necessarily need to use GPUs to deploy a Gen AI model. As a general rule of thumb, I'd say if your model is, say, less than 30 billion parameters, it might be worth investigating using CPU for serving a model. Again, there's more that you need to think about here. What's acceptable latency for your customers? Is CPU-based inference meeting that benchmark? If it isn't, obviously that's a moot point, and you probably want to use an accelerator. The accelerator could be a GPU, or it could be even a neuron device, depending on what the use case is. Another key consideration if you do choose to deploy when you're deploying your Gen AI model with ECS is how do you actually load the model into your application. Gen AI models can vary immensely in size. Some of the larger ones can be tens or hundreds of gigabytes. Even the smaller ones would be several gigabytes. So you probably want to get them loaded onto the host as fast as you can so that your application is up and running, your model is up and running and responding to requests as soon as possible. There's kind of three key ways you could do that. One, you could use EFS, which is a fully managed scalable file system. You can host your model on EFS and make that and serve that to your application deployed on ECS. You could just host your model on S3 and use S3 APIs in your model code or in your container to pull the model at runtime. Or you could even bundle the model into the container image itself and make a massive 5, 10, 20 gigabyte deployable. Of these, my recommendation would be to use Amazon S3. I would suggest don't do a simple get object call. There's ways to make S3 more performant, and there's a lot of literature about how you can pull objects from S3 more efficiently. And I'd recommend going through those if you're deploying a Gen AI model on ECS. I already spoke about scaling out your model, your Gen AI application, but you also probably want to auto-scale your model server deployed on ECS. Same set of capabilities. You can scale on any metric of your choice. It can be a custom metric, predefined metric, ECS metric, doesn't matter. One additional dimension, if you do choose to deploy with accelerated compute on EC2, is that you also need to configure auto-scaling for your model, for your underlying infrastructure. If you choose to do that, I'd recommend looking into using worm pools, which can really help accelerate startup time so that your scale out can be more efficient, especially when you're starting to scale and trying to get the most juice out of your GPU accelerated machines. Finally, in terms of monitoring, ECS offers a rich set of monitoring capabilities. You get container insights out of the box, which gives you a ton of metrics about your ECS workloads. You get Firelines, which you can configure in your task definition and use that to send logs to CloudWatch logs, to any partner destination, or basically anywhere that you want to. One key call out I would have here would be to deploy an X-ray sidecar for your GenAI application. It's usually a good idea it's a good idea to trace user requests end to end because it can help you debug things, help you identify bottlenecks in your application end to end. This isn't a native integration, so you would need to deploy the X-ray daemon as a sidecar. But there are good patterns to how you can deploy the X-ray daemon on your application. Finally, in terms of security is one of the places where I think ECS, and particularly ECS with Fargate, really shines. Your applications by default on ECS Fargate are isolated. Each task you deploy on ECS Fargate runs on its own VM, so there's no chance of a breakout in your container causing any security issues for other applications that you've deployed. A new capability we just recently launched is an integration with GuardDuty, which allows you to have runtime threat detection for your containers running across ECS on EC2 as well as Fargate. That's a one-click integration. It's a quick plug. If you're a security-sensitive customer, do give that a spin. Might be useful. And with that, I'll hand over to Mridula.
Thank you. All right, quickly wrapping up, let's take a look at how some of the customers are using Amazon ECS or Fargate to run their GenAI applications. First one is Scenario. It's a game development company and wanted to reduce their time to market for game studios by using generative artificial intelligence to create style-consistent assets. And they used Amazon ECS, a fully managed container orchestration service, to build its generative AI offering. And an interesting fact is that they wrote the first line of code on October 2022 and built the beta in 2 months with just 3 engineers. So Scenario was able to generate over 1 million images in the first 2 weeks and are continuing to rapidly use Amazon ECS and scale and grow on AWS. Second startup company as well, Rad AI, is a SaaS company that aims to increase the quality of healthcare by streamlining radiology workflows using natural language processing. When they came to AWS, they were deploying ML applications on data centers on-prem and were looking for higher performance and faster inference speeds in terms of serving more customers. In addition to migrating their ML models to Amazon EC2 P4D instances powered by NVIDIA, Rad AI was able to streamline their experimentation by deploying their ML models on Amazon ECS and have set up their CI/CD, so they were able to experiment, develop, train, and deploy their models much quickly using PyTorch frameworks and are able to strengthen customer satisfaction by incorporating the feedback quickly and increasing the inference speeds by 50%. Actuate is a cloud-based computer vision platform that ingests vision feed from remote accessible cameras and detects security threats in real time. Their application decodes video streams into JPEG images and sends those images to the AI models for instant analysis. In order to be efficient, Actuate was looking for dynamic capacity scaling to meet the peak resource performance requirements. And to do all of this in a cost-effective way, they chose ECS Fargate as the operating model to manage their EC2 instance, so that the management of EC2 instances is completely abstracted away from the customer. And Fargate containerized subsets of cameras that incorporated internal scheduling logic and launched tasks at specific times on a daily basis. And this enabled them to achieve improved CI/CD and streamlined monitoring and troubleshooting for continuous improvements. Quick takeaways for all the talk that we did. The first one is generative AI foundation models can be used for a variety of applications. So keep in mind that when you start with a foundation model, it can be used later for a downstream of tasks. Second one is generative AI applications aren't inherently unique. The key nuance is that how the application integrates with the model. So the prompt engineering and using RAG for best results, as Vibha pointed out, would be the way to go. And use Amazon Bedrock for model serving and use Amazon ECS with AWS Fargate as your application server to get started quickly. And then Amazon ECS offers both accelerated, which is in the EC2 form, and serverless using the Fargate launch type compute options as a rich feature set for self-hosting.
I'll do a quick plug here, Mridula. So the biggest takeaway for me here would be personally if this talk helps demystify Gen AI applications for you somewhat and encourages you, for those of you who haven't tried already, to try out building Gen AI apps on AWS. It's not rocket science for the most part. A lot of the hard part, I think, is solved for, and really the world is your oyster, so to say. And it's a good time to start testing out with new use cases if you haven't already.
Thank you. And in addition to the takeaways, here are some references that you may want to infer to in terms of blog posts or collateral with turnkey solutions in terms of how you want to get started. With that, I hope that this talk was useful for you and you're moving out from the room confidently to make your journey more successful and pace through your Gen AI path forward in a more accelerated way. Thank you so much.
Thank you.